stacks of technical sources, articles, research papers, field manuals, and distill them down into the core knowledge you need to be instantly and thoroughly well-informed. Today, we are taking a massive detour from the theoretical and diving into the hyper-practical yet utterly fascinating world of automotive refinishing.
It really is.
When most people think about painting a car, they picture a quick blast of color and clear coat. But what we've learned from our sources is that high-fidelity refinishing isn't just painting. It is a rigorous, demanding convergence of precision craftsmanship, chemical engineering, and material science.
It is.
If you miss one microscopic detail, the entire multi-thousand-dollar job fails.
That is the core of our mission today. We are extracting the critical protocols required to restore a vehicle's aesthetic and, crucially, its protective integrity back to original equipment manufacturer, or OEM, standards.
Right.
And we really need to stress this from the jump. The process is not about applying liquid color. It is a meticulously managed chemical transformation.
A transformation.
Exactly. Liquid coatings become solid, cross-linked films. And if you fail at any foundational stage, whether it's, chemical decontamination, sanding geometry, or solvent management, you build a mechanism for catastrophic failure months down the road.
It's just inevitable at that point.
It's chemistry's law.
And we are not dealing in hypotheticals here. Our sources give us a deep dive into 4 specific, industry-leading systems that define this process, giving us the full picture from the metal up.
Right. On the mechanical front, we are looking at the foundation laid by 3M Cubitron abrasive technology. This completely redefines the quality of the scratch pattern, the literal tooth we give the metal for things to stick to.
Then we make a hard pivot into chemical purity using the Axalta surface preparation systems. This is the ultimate bond insurance against all those unseen enemies.
That's a great way to put it. And for the color, the aesthetic heart of the repair, we analyze the application mastery required for Cromax XP solvent-borne base coat. We'll be focusing specifically on the critical challenge of flake orientation and metallic control.
And finally, the durable protective shield. Nason 465000, SelectClear High Solids Clear Coat. We're looking at how to maximize gloss and durability while navigating the complex physics of solvent entrapment.
It is a comprehensive technical roadmap. Every single step is governed by chemical rules.
Okay, let's unpack this, starting exactly where this chemical magic has to take place. The strictly controlled ecosystem, the paint booth.
The paint booth is, well, it's often treated as just a big, expensive fan and heater.
Right.
But it is so much more critical than that. It is the vessel for the transformation. It is the only place in the shop where temperature, humidity, and most importantly, airflow are engineered to allow liquid coatings to cure correctly.
So if the environment is unstable,
then the chemicals just cannot perform their required job. It's that simple.
The technical manuals we reviewed keep using this term laminar flow as the gold standard. For someone who hasn't been in this world, what does laminar flow actually mean, and why is it so essential for a flawless finish?
Laminar flow is the ideal state where air moves uniformly and consistently, usually in a direct downdraft pattern. From the ceiling, filters directly to the floor or wall exhaust.
Okay.
Think of it like a curtain of invisible, clean air just enveloping the vehicle. The air moves across the panel surface and carries overspray and evaporated solvents away without causing any turbulence, any swirling, or eddies.
And if that flow breaks down, if it becomes turbulent, what's the immediate consequence?
Well, if the air swirls, you have a major issue. One, the overspray that was supposed to be carried away can be pulled back down onto the wet paint film,
causing dirt and texture issues.
Exactly. Rough texture, dirt inclusions. Two, and this is most critical for our Cromax XP metallic system, turbulence disrupts the consistent evaporation rate of the solvents in the base coat. This physically disturbs the precise alignment of those microscopic aluminum flakes.
So the air literally messes up the reflection properties of the paint itself.
It does. It directly leads to mottling or clouding. That's why airflow control is job number 1. And directly linked to that is pressure management.
Right. Maintaining a slight positive pressure inside that booth. Why is that so non-negotiable?
This is a fundamental contamination defense mechanism. It's usually monitored by a precision instrument called a manometer. The booth must maintain a slight positive pressure differential relative to the outside shop environment. This means that if you crack a door, or if the seals are slightly worn, air must flow out.
And what's the high-stakes risk of letting the pressure drop to 0 or, God forbid, going negative?
If the pressure drops, the booth immediately starts sucking air in from the outside shop. And what does the shop environment contain?
Everything you don't want.
grinding debris, welding dust, paint fibers, sanding particulate-heavy contamination that will be vacuumed directly onto the freshly prepped panel or the wet base coat.
So every one of those particles.
Costs time and material to fix, or worse, guarantees a visible flaw in the final clear coat.
It's horrifying to think that a tiny imbalance in air pressure can turn your pristine booth into a high-powered vacuum cleaner for shop junk.
Absolutely, and this brings us straight to filter integrity, which is where this system is most vulnerable to real-world failure. Filters are sacrificial, they hold contamination, and as they load up, their resistance to airflow increases dramatically.
Okay, so let's start with the intake filters, the ones usually on the ceiling. They're the last line of defense for the air coming in.
Right. The intake filters are designed to diffuse the air, to make that gentle laminar flow uniform. If they become clogged, they increase resistance, reducing total airflow.
Okay, that makes sense.
But the catastrophic risk is when they are damaged or just overloaded. They can physically release accumulated dust that has settled on them, dust that falls directly onto the roof or hood of the vehicle.
Which are often the most visible, least forgiving surfaces.
The absolute worst places for it to land.
And the exhaustion side, the filters in the floor or walls, their failure mode is almost worse for metallics, isn't it?
It is. Clogged exhaust filters, which capture the bulk of the overspray, they just choke the system. If the exhaust fan can't pull air out effectively, the internal pressure of the booth spikes.
As we discussed.
Right. And even if the pressure remains positive, the velocity and, more importantly, the uniformity of the airflow are destroyed. This turbulence hits the wet metallic base coat, leading directly back to the modeling problem.
So the booth environment is chemically damaging the finish.
Yes. That correlation, clogged exhaust filters equals turbulence equals destroyed metallic flake alignment, is a perfect illustration of how interdependent these systems are.
It connects physics and chemistry immediately.
It does. Now, let's look at the contamination control protocol inside that booth. Our sources are very, very explicit about daily maintenance, especially the absolute prohibition against using compressed air to clean up.
I can just picture the old school mechanic in the shop who thinks he's being fast and efficient by grabbing the air gun and blowing the dust out of the corners. What is the fundamental immediate risk there?
That is an SOP violation that costs jobs. Plain and simple. The protocol requires daily sweeping or vacuuming with specialized, explosion-proof equipment. When you use compressed air, you take heavy particulates, metal filings, dried paint chips, heavy fibers that were harmlessly resting on the floor, and you loft them. They become suspended and airborne.
So they just hang in the air.
For hours.
Yeah.
Unlike lighter overspray, these heavy particulates remain airborne for hours, guaranteeing dirt inclusions in every subsequent job until they finally settle again. You trade 5 minutes of sweeping for 2 hours of guaranteed contamination.
It's so counterintuitive. You think you're cleaning, but you're just activating the contaminant.
Exactly. We also have to address moisture management. We know a common technique is wetting the floor to trap heavy dust. But you must be incredibly cautious, especially since we are dealing with solvent-borne systems like Cromax XP.
What's the specific chemical caveat there regarding standing water and solvent-borne coatings?
Well, while a damp floor can trap dust, excessive standing water dramatically spikes the relative humidity, the RH, inside the booth. Solvent-borne coatings, like Cromax XP, are designed to have solvents flash off at a precise rate. High humidity retards that flash time. The solvents take much longer to evaporate.
Which throws the whole process off.
It throws off the entire curing process, potentially leading to solvent entrapment, slowing the setup of the base coat and affecting how the final clear coat flows. You've guaranteed one type of defect while trying to solve another.
And the walls themselves are not passive. I was surprised to read they can actively contribute contamination, if not maintained.
Oh, absolutely. Think about the booth walls and the viewing glass. They accumulate layers and layers of dried overspray over time. As the booth cycles through its operation, heating up to 140 degrees or for baking and then cooling down, that thermal expansion and contraction causes those rigid layers of dried paint film to degrade and delaminate.
They just flake off.
They flake right off the walls and fall onto the fresh, wet vehicle.
That is a maintenance nightmare.
It is, which is why the sources recommend preventative measures like peelable booth coatings. This is a sacrificial layer you apply to the walls that traps the ambient dust and overspray.
And when it gets too loaded?
You just strip the entire layer off the walls like wallpaper and reapply a fresh coating. It ensures the ecosystem is consistently pristine.
Finally, before we move on, what about those door seals and plenum gaskets? They seem so minor, But if the booth is a sealed ecosystem, they are the weakest link.
They are constantly being assaulted. They're exposed to solvent vapor, heat from the bake cycles, physical wear. They degrade, they crack, they compress over time.
And if a gasket fails?
It allows unfiltered air to bypass the entire elaborate filtration system we just discussed. It's a direct, unfiltered stream of environmental contamination straight onto your high-precision job.
So you can have the best filters in the world, but if the gasket is leaking, you have a security breach.
A total breach.
We've established the pristine environment. Now we move on to the panel itself. The sources are definitive. The entire longevity of the repair, the protective integrity, is dictated by the quality of the mechanical and chemical bonds formed right here at the substrate level.
This is where we lay the foundation, and it begins with how we abrade the metal. We are talking about mechanical keying, and that requires moving beyond standard sandpaper and introducing the mechanical advantage of 3M Cubitron abrasive technology.
And it's precision shape grain, or PSG.
Precisely.
Okay, that sounds a little bit like marketing speak. But our sources treat PSG as a fundamental leap forward. How does it physically change the way we key the surface compared to traditional ceramic abrasives?
It's a huge difference. Traditional abrasives are essentially crushed, irregularly shaped ceramic chunks. When you run them over the surface, they don't cut cleanly. They plow through the material, tearing it and generating a huge amount of friction and heat. PSG, however, is a triangular engineered grain. It's uniformly sized, stacked neatly, and designed to self-fracture, constantly presenting fresh, sharp edges to the material.
So it's like a tiny self-sharpening knife.
That's a perfect analogy. It acts like a series of microscopic knives slicing through the metal or the body filler rather than plowing. And the immediate benefit is twofold: a cooler cut and a cleaner scratch.
And why is reducing that heat input so crucial in a modern body shop?
Heat input is a major enemy. Modern vehicles use high-strength steel HSS, which is highly susceptible to warping under localized heat stress.
Right.
By slicing, Cubitron minimizes the thermal effect, reducing the risk of panel distortion. And furthermore, less heat means less swelling of the feather edges in the repair zone.
So the existing paint doesn't lift.
Exactly. It doesn't lift or expand unevenly as you sand. It results in a far more predictable and stable substrate.
Now, before we even touch a PSG disc to the metal, we have to tackle the mandatory first step: chemical pre-cleaning. I think most people, even some professionals, skip this, assuming the sanding will clean the surface. Our sources treat this omission as a guaranteed failure point.
It is mandatory. Sanding a dirty surface is perhaps the #1 avoidable error. If you start sanding over a panel contaminated with waxes, silicones, road tars, oils, or salt residue, the abrasive drives those contaminants deep into the scratch pattern.
Locking them in.
It locks them into the microscopic valleys of the substrate. And once embedded, they cannot be reliably cleaned out and become the prime cause for defects later on.
So the first line of defense is the pre-wash phase, using hot water and detergent. And this isn't just about general dirt. It's about neutralizing a very specific chemical enemy that solvent cleaners just can't touch.
We're talking about salts. This is a critical deep dive detail. Salts from road brine, or more commonly, the salts contained in human perspiration from the technician just touching the panel, are water soluble.
And solvents won't touch them.
They are completely impervious to the solvent-based degreasers we use later. If you don't remove the salt first, it stays.
And why is that microscopic speck of salt so dangerous to a coating that is supposed to last 10 or 15 years?
Because salt residue acts as a hygroscopic nucleus. Hygroscopic means it strongly attracts moisture.
I see.
Even after the paint is applied, primer, base coat, clear coat, the film is never perfectly impermeable. Over time, that tiny speck of salt residue under the paint starts drawing moisture through the coating.
How?
Through the process of osmosis. It acts like a tiny chemical pump, pulling water from the atmosphere into the interface between the substrate and the coating.
You're telling me a perfect, flawless paint job can be destroyed by an invisible salt particle that causes water to pool underneath it months later?
That is the precise chemical mechanism of osmotic blistering. The paint film lifts off the substrate in a pattern of small bubbles months after the customer has taken the car home.
Wow.
Removing salts with hot water and detergent is the absolute non-negotiable insurance policy against this devastating long-term failure.
That puts into perspective the scale of precision we are aiming for. Okay, so once the panel is chemically neutral, we move to the physical task of paint removal and body filler preparation.
Yes. Areas needing structural body filler must be restored to bare, coarse metal. Our sources recommend the 3M Cubitron 2F'er fiber roll-lock disc, grade 80+ game. We need that deep tooth for the filler to mechanically bond.
And what's the significance of that plus rating on the Cubitron abrasive? I saw that a few times.
The plus fair rating signifies an efficiency improvement. An 80-plus disc performs the aggressive material removal rate of a coarser traditional grit, maybe a P60.
Okay.
But it leaves the refined scratch profile of a true P80. This allows the technician to strip the coating quickly and establish a strong mechanical key for the filler without unnecessarily thinning the panel or creating overly deep random scratches that are hard to remove later.
Got it. Once the filler is applied, the work shifts to sculpting and refining the shape, which requires moving through a deliberate sanding progression. The source insists on the 100 rule.
This is the rule that prevents sand scratch swelling. If you skip too many grit numbers in one jump, say, going from P80 straight to P320, the deeper, coarser scratch pattern remains beneath the surface.
And then the solvents get in.
Exactly. When the primer or top coat is applied, the solvents soak into those deep valleys. As the solvents flash and the coating cures, it shrinks, but the deep scratches swell, telegraphing the coarser pattern right through the final mirror finish.
So you must meticulously step up the process. Walk us through the required steps to get from rough shaping to a stable primer substrate.
Step 1. Rough shaping, using the P80 Plus can. A guide coat, a powder that highlights high and low spots, is crucial here. You're establishing the body line, sculpting the major shape.
Right.
Step 2 is refining, moving to 120 plus or 150 plus to start removing the P80 marks.
And the final filler finish is the absolute threshold.
It is. The filler must be finished with P180 plus bunker. The rule is absolute. Scratches coarser than P180 are simply too deep for standard high-build primer surfacers to fill reliably without shrinking and telegraphing later.
So the painter has to trust that the panel is P180 flat before they even pull the primer gun trigger.
That's the handoff, exactly.
Finally, the feather edge. This is the transition zone between the repair and the surrounding OEM paint. How do we create a transition that doesn't map or show up as a visible ring?
This requires finessing the edge. You need 220 plus or 320 plus on a dual action or DA sander, but critically, you use a soft interface pad. The pad cushions the abrasive, allowing it to gently taper the edge, creating a microscopic, gradual ramp rather than a hard step.
And if you leave that hard edge,
The primer and paint layers will just accentuate it, and you will see a faint visible ring in the final product, the phenomenon known as mapping.
we have a mechanically stable surface, finished to P180 plus N. We apply the primer surfacer to fill those refined scratches. Once cured, we move to the final block sanding. And this is where we hit what you called the aha moment regarding the specific color we are using, metallic versus solid.
This is perhaps the most critical distinction in substrate preparation. It really is. If you are spraying a non-metallic solid color, P400 grit is generally acceptable for the primer finish.
Okay.
However, if the job calls for a high metallic or pearl color, like our Cromax XP system, the primer must be finished with P600 grit, either wet or dry.
P600 seems almost polished. For a metallic finish, that seems excessive.
Right.
Why does the difference between P400 and P600 matter so intensely for the structure of the final paint job?
This is pure material science. Remember those microscopic aluminum platelets we call metallic flakes?
Right.
A P400 scratch pattern creates deep enough valleys that those aluminum flakes, which are trying to align randomly for a uniform reflection, will physically settle into the valleys of those scratches.
And when they settle, what happens?
They align linearly. They follow the direction of the P400 sanding marks. When the clear coat is applied, the solvents soak in, and the underlying material swells, highlighting these linear flake patterns.
Yeah, that's what you see.
That's what you see. When light hits the finished panel, it reflects inconsistently off the linearly aligned flakes, making the sand scratches visible through the clear coat.
So that's the real mechanism of sand scratch swelling.
That's it. That's the linear modeling. P600 creates a substrate so flat that the flakes have nowhere to settle or hide, forcing them to remain randomly oriented.
That's fascinating. The aesthetic flaw is driven by a microscopic structural failure in the foundation. It forces that extra step of refinement.
It's non-negotiable for high-fidelity metallic matching. And this refinement extends to the adjacent blend panels, too. Those need even finer abrasion P1000 foam blending discs or a gray Scotch-Brite pad, just enough to create microscopic surface area for the new clear coat to adhere without visibly damaging the OEM finish.
The panel is now mechanically flawless. Now we pivot entirely to the Axalta chemical decontamination protocol. And our sources remind us that a car that looks clean is rarely chemically clean.
This is the final barrier against fisheyes and delamination. We have to neutralize all organic and polar contaminants, and this requires the rigorous two-cloth method. This protocol is mandatory for every chemical cleaning stage.
Okay, describe the method and tell us why the timing is so critical.
The two-cloth method is a physical process designed to lift and remove contaminants, not just dissolve them. You need one cloth, saturated with the specific cleaner, whose job is to aggressively dissolve the grease or silicone and hold it in suspension.
And the second cloth follows right behind.
A second dry, lint-free cloth, often a high-tech material like Sontara, must follow immediately.
Why immediately? Why is that so important?
You must wipe the surface dry before the solvent on the panel can air dry. If you allow the solvent to evaporate, the physics dictate that the dissolved grease, oil, or silicone, the contaminants the solvent was holding, are redeposited back onto the surface.
Oh, so you're just spreading it around.
You've spread it over a much larger, thinner area than before. You've just diluted the poison and spread it. The dry cloth physically removes the liquid solvent and the dissolved contaminant before redeposition can occur.
That is a phenomenal detail. It explains why a seemingly clean panel can still produce fish eyes. So let's look at the 3 mandated steps in the Axalta system. Step 1 handles the heavy organic stuff.
That's the solvent-borne pre-cleaning, using non-polar solvents like Axalta 399LS Prep-Sol or Axalta 200 Silicone Remover. These are designed to tackle the thick organic contaminants oil, heavy grease, waxes, and silicones.
And you do this away from the booth.
The sources advise doing this away from the immediate spray zone, usually in the prep station, because dissolved silicone tends to migrate easily. You don't want those vapors hovering over your final spray area.
Step 2 targets the other side of the chemical coin.
Step 2 is the waterborne final cleaning, using products like Axalta 210 or 220. This targets polar, water-soluble contaminants that solvent cleaners leave behind.
So this is where we get the last of the salt.
This is where we catch tree sap residue, insect proteins, and, most importantly, the residual human perspiration and salts that survived that initial hot wash.
This sounds like the final line of defense against osmotic blistering.
It is the ultimate insurance policy. It guarantees a neutral, non-hygroscopic surface. If you skip this, you're gambling with long-term adhesion.
And step 3 is the ultimate pre-gun check.
The Axalta 9145 Anti-Static Final Wipe. This addresses the problem of static charge, which is generated simply by masking the vehicle, wiping it down, or handling plastic parts.
So the panel becomes a dust magnet.
Exactly. It turns into a magnetic field, attracting airborne dust just as the painter is ready to shoot. The 9145 uses conductive agents and alcohols to neutralize the surface charge, allowing any last dust particles to fall away from the panel. It ensures a clean trigger pull.
The surface is perfect. P600 flat, neutralized and anti-static. We are finally ready for color. Axalta Cromax XP solvent-borne base coat. The goal here is achieving full opacity and the correct color orientation, the metallic flop, without building excessive film thickness.
And we have to start with the delivery mechanism. The spray gun. The sources specify the Devilbiss DV1, a high-efficiency gun, and its configuration is extremely rigid for metallic control.
What are the key hardware and pressure settings for this metallic base coat?
Well, the preferred air cap is the DV1B or possibly B+ Sure, which provides a softer, well-distributed plume of material. The pressure setting is absolutely critical, 2022 psi or 1.4, 1.5 bar.
And that's measured at the gun.
Measured at the gun inlet with the trigger fully pulled. The pressure dictates atomization. If you go too high, you atomize the paint too finely, which typically lightens the metallic color.
That's facing.
And too low, you get poor distribution and modeling.
The chemistry setup is next. Reducer selection dictates the entire process.
It does. The mixing ratio is a strict 2.1 color to reducer. The reducer is the solvent, and its evaporation rate is matched directly to the shop temperature. The painter must choose the correct number. XP1060 is fast for cold shops, around 65 degrees Fahrenheit, while XP1090 is very slow for hot shops, near 95 degrees Fahrenheit.
So using the wrong speed reducer is a guaranteed defect.
It is. If you use a fast reducer in a hot booth, the paint solvents evaporate midair before the paint even hits the panel. The result is dry spray, a rough, textured, dusty surface.
And the other way around.
A slow reducer in a cold shop means the paint stays wet too long, risking runs and allowing the metallic flakes to clump, which causes mottling.
Now, what about that intriguing chemical modification? Adding a small amount of clear coat activator to the base coat. It turns it into a catalyzed system. Why would you want to introduce cross-linking into the base coat layer.
It is a major durability enhancement, turning it into a catalyzed enamel system. The sources recommend adding 1 ounce of Cromax Clear Coat Activator per ready-to-spray quart.
Okay.
The activator allows the base coat resin to begin a limited cross-linking process. This dramatically improves intercoat adhesion, the chemical bond between the base coat and the clear coat, and most importantly, increases stone chip resistance.
So it makes the whole system tougher.
Much tougher. If a stone hits the catalyzed base coat, the film is harder and less likely to flake or chip down to the primer.
It's reinforcement for the entire system, not just the clear coat.
Yeah.
And this level of precision means a viscosity check is mandatory.
Absolutely. The target is 15-17 seconds and is on #2cup. This is the precise thickness required for the metallic flakes to float and orient correctly. Too thick and they are restricted. Too thin and you lose coverage and risk runs. You cannot eyeball this.
Moving to application technique, that 4-6-inch gun distance and the mandatory overlap.
Right, you hold the gun 4-6 inches away, moving parallel to the panel. The overlap is crucial, 50-75% overlap.
And if a painter only overlaps by 25%?
They leave a gap where the material is thinner and drier. Since the center of the fan pattern lays down the wettest, densest material, inadequate overlap guarantees striping or tiger stripes.
Because the dense center lines will appear darker.
Exactly. A generous overlap ensures uniform material deposition.
We aim for 2-3 medium wet coats until hiding, but the flash time protocol between these coats is essential for chemical integrity.
Flash time is scheduled solvent escape. Between coats, we need 5-10 minutes. The visual check is key. The glossy wet film must transition to a dull, matte finish.
What happens if you rush that?
If you rush, trapped solvents will cause lift or blistering when the next coat is applied. If you wait too long, say over 24 hours, the resin fully shrinks and hardens, and you lose the necessary chemical bite for intercoat adhesion.
So you'd have to sand the base coat and restart.
You would.
Let's discuss the drop coat or effect coat. This feels like where the art comes in for these metallic systems. What is its specific purpose and how does the technique differ from the color coats?
The drop coat is the final act of alignment. It's the correction coat. During regular color coats, the high pressure and close proximity can force the metallic flakes to align too uniformly.
Creating that dark flop or light phase.
Right. The drop coat equalizes this.
So how is it applied differently?
You apply a final, quick mist coat immediately after the last color coat has flashed. You change 3 things. First, increase the gun distance significantly to 8-10 inches. Second, reduce the inlet pressure slightly down to 18-19 psi. Third, move the gun faster.
And what did that do?
This combination creates a drier, softer plume of paint. When it lands on the surface, it doesn't disturb the underlying wet film. Instead, it gently drops the flakes to settle randomly. It eliminates striping and halo rings and achieves the final, uniform color appearance.
It turns mechanical application into chemical randomness.
That's a perfect way to describe it.
The stakes are incredibly high here. Even with meticulous technique, small variables, a slightly cooler booth, a quick rush on the flash time, can lead to major flaws. Let's use the source material to diagnose the specific root causes of the most common base coat failures.
Yes, this section is about understanding that defects aren't random. They are evidence of a failure in protocol.
Let's start with modeling, or clouding. We know it involves flakes, but what is the specific root cause?
The root cause is uneven metallic distribution because the film stayed wet too long. This happens because the base coat was applied too heavily, the gun was held too close, or, crucially, the reducer was too slow for the ambient temperature.
So the flakes have too much time to move around.
They swim and clump together unevenly. The remedy is to ensure you select the correct, faster reducer and apply a final, lighter, drier coat to help reorganize those flakes.
Okay, how about striping? The dreaded tiger stripes.
Striping is a technique issue. The root cause is inconsistent overlap, falling below that critical 50-75% or a dirty, distorted spray pattern. The density difference between the heavy center of the fan and the lighter edges creates those visible dark bands.
And the fix.
Prevention is adhering strictly to a 75% overlap. The remedy is applying a cross-coat spraying perpendicularly followed by the necessary drop coat to smooth the transition.
Fish eyes. The classic sign of contamination.
Fish eyes are strictly surface contamination, silicone, oil, or grease. The paint cannot adhere to the contaminated spot, and surface tension causes it to pull away, leaving a crater.
And the prevention is that rigorous cleaning protocol.
The Axalta 2002-20 protocol with the two-cloth method. If they appear during spraying, you can try applying very light mist coats to slowly bridge the eye, but severe fish eyes require sanding down and restarting.
Let's revisit sand scratch swelling. If a painter sees linear marks appearing through the clear coat, where did they fail in the process?
That failure happened hours or even a day earlier in the prep station. The root cause is foundational. The primer was sanded with too coarse a grit P320 or P400 when a metallic color was used.
And the flakes settle in the scratches.
The solvents swell those deep scratches, and the metallic flakes act as mirrors, reflecting the linear flaws. The prevention is that mandatory P600 finish for metallics.
And there's no easy remedy for that one.
No, the remedy is the hardest one. Stripping the paint down to the primer, resanding to P600, and refinishing. There is no saving a deep scratch once the base coat has been applied.
What if the color simply isn't covering poor hiding, even after 2 or 3 coats?
Poor hiding means insufficient opacity. The root causes are often over-reduction, which spreads the pigment too thinly, or just not enough coats.
Okay.
But a major cause, often overlooked, is using the incorrect undercoat color, or value shade. If the sealer or primer shade is too far off the final color, say a light gray sealer under a very dark metallic black, you will need excessive base coats, risking film thickness and solvent entrapment.
The remedy is just more coats then.
Check your viscosity first, but yes, apply additional coats until that black and white spray-out checkerboard disappears entirely.
Dry spray. We touched on this with reducer selection, but what's the technique failure there?
Dry spray is caused by the gun being held too far away, more than 10 inches, or using a reducer that is too fast. The solvent evaporates before the paint droplets can flatten and level on the panel.
The paint essentially powders onto the surface.
That's right. The remedy is to gently tack or nib sand the affected area with P1000 and apply a final wet coat with corrected settings.
And finally, color mismatch. If the color is off, how often is it the paint itself versus the painter's technique?
In metallic systems, technique is often the issue. Incorrect spray pressure is a huge factor. Higher pressure atomizes the flakes more aggressively, causing the color to look lighter or face.
Low pressure.
Keeps the flakes flatter, making the color look darker or floppy. This is why test card spraying is mandatory. You spray the card using the exact pressure settings you will use on the car.
So the painter knows what to expect.
They know if they need to adjust the pressure or the amount of blending on the vehicle.
We have achieved the perfect color. Now we seal it with the Nason 465-000 SelectClear. This is a high solids or HS urethane clear coat. Why is the fact that it is high solids so important, and how does that change the application challenges?
High solids means it contains a higher volume percentage of resin material and a lower volume of solvent compared to older medium solids, or MS, clears.
So it's thicker.
Much thicker. The benefit is superior protection. You achieve a much thicker, more durable, dry film thickness in fewer coats. The challenge, however, is that viscosity.
Okay.
HS clears are inherently much thicker, and because the film build is so high, controlling the escape of the remaining solvents becomes the primary concern.
Before we shoot the clear, the final surface inspection, the gentle tack wipe.
After the 15-20 minute flash time of the base coat, we use a high-quality tack cloth to lift any dry airborne dust. But the protocol comes with a vital warning. Do not press hard.
Why not?
Tack cloths are slightly impregnated with resin to capture dust. If you press too hard, that resin transfers to the delicate, matte base coat surface, causing tiny defects or spots in the final gloss finish. It must be a gentle, feather-light action.
And dealing with dirt nibs that may have settled in the base coat.
If you spot a dirt nib, you can carefully denib it using P1000 dry sandpaper. But here's the trick of the trade. You must remist the sanded spot with a quick, light burst of base coat.
Oh, you can't just clear over the sanded spot.
You should never clear coat over a sanded scratch, even P1000 in the base coat. The clear coat will magnify that scratch, and it will be visible in the final product. Recoloring the spot blends it back into the field before the clear.
Now let's talk chemistry. The mixing ratio for Nason 465-000, SelectClear, and the cross-linking process.
We are initiating a chemical cure. The ratio must be precise. 2 parts clear, 1 part activator, 20% reducer. The activator starts the hardening process, the cross-linking of the polymer chains, so the 2.1 ratio is non-negotiable for hardness.
But that 20% reducer requirement.
That's where most failures occur if protocols are ignored.
I want to focus on that 20% reducer. If the clear is already high solids, why is adding 20% more solvent, the reducer, absolutely mandated by the source material?
Because of the high viscosity. If you skip the 20% reducer, the clear coat is just too thick. When you apply it, it resists leveling and flow out, resulting in heavy, textured orange peel.
And that's not all.
No. Furthermore, without the reducer thinning it down, the two mandated coats will be excessively thick. The reducer lowers the viscosity, allowing the clear coat to relax, flow out, and level into that desired mirror-like finish before the cross-linking cure locks the structure into place. Skipping it is sacrificing gloss and smoothness.
The required pressure also increases for this heavier material, correct?
Yes. We shift to a clear coat-specific air cap, and because the resin mixture is heavy and viscous, we need higher pressure to atomize it effectively. 28-29 psi at the gun inlet. This ensures the droplets are fine enough to achieve maximum flow and gloss.
The coat strategy is 2 coats. Walk us through the timing and the purpose of each.
First, you apply a medium-wet foundation coat. It should look smooth, but not yet fully glossy. This sets the stage for adhesion. Then comes the critical flash time, 5-7 minutes.
And this is the razor's edge of the entire process.
It is.
Why is that 5-7 minute window so critical, and what are the failure modes on either side of it?
You are balancing immediate solvent escape with intercoat adhesion. If you rush the flash time, say, 3 minutes, you trap bulk solvents between the first and second coats. When those trap solvents try to escape later, they boil, causing catastrophic solvent pop.
And if you wait too long?
If you wait too long, say 15 minutes, the first coat starts to set up too hard and the second coat cannot chemically knit or bond effectively to it, leading to a high risk of long-term delamination.
So how do you check it?
The touch test is key. It should leave a visible fingerprint on the masking tape, but the clear should not pull a string of wet material.
After the flash, we apply the full wet coat.
The second coat is the full wet coat, flowed out to maximum mirror gloss. And our sources give a strict film limit here. Do not apply more than 2 coats, which equates to about 2.0 mils DFT.
And exceeding that thickness guarantees defects.
It guarantees them. A film too thick traps an enormous amount of solvent deep inside, leading to latent failures like dieback or severe solvent pop hours after application.
Finally, curing and buffing. When is the job truly stable?
It's dust-free in about 30 minutes at 70 degrees Fahrenheit. If you air dry, it requires 12-24 hours, so overnight, before it is hard enough to safely buff.
And if you buff it too early?
Buffing soft clear coat will create deep, permanent swirls. If you force dry or bake, the target is 30 minutes at 140 degrees Fahrenheit temperature.
And there is that critical safety measure before hitting the heat.
Yes, you must allow a mandatory 5-10 minute flash off before turning on the heat. This is non-negotiable. If you immediately bake a thick, fresh film of clear coat, the solvent load inside the film is superheated and boils violently,
Leading to massive solvent pop.
a massive panel-wide solvent pop failure. You have to allow the surface to start setting up and the bulk solvents to dissipate before applying heat.
The shift to high solids means we're fighting a different set of demons, chemical failures, linked to solvent management. Let's tackle the biggest failures that plagued the Nason 46500 system.
We need to focus on what happens when the cross-linking process is disrupted or the solvents are managed incorrectly.
We'll start with the most common and most visually frustrating, solvent pop.
Solvent pop is the sign of trapped solvent boiling. It manifests as tiny bubbles or pinholes. The causes are always one of 3 protocol failures: rushing the critical 5-7 minute flash time, skipping the 5-10 minute pre-bake flash off, or applying excessive film build more than the recommended 2 coats.
And the fix is not easy.
No. Prevention is simple adherence to time and thickness limits. If the pop is minor, sometimes light sanding and a quick re-clear is possible, but if the pinholes are deep, you must sand down to the base coat and re-clear the entire panel.
Dieback, or loss of gloss, is one of those defects that haunts a painter days later. The job looks perfect and then the gloss fades.
This is a delayed chemical failure. Dieback occurs when the clear coat looks glossy immediately after application, but hours or days later it turns dull or hazy. The root cause is solvents trapped deep in the film.
Because it was too thick.
The film was too thick or the viscosity was too high, meaning the painter skipped the 20% reducer. Those trapped solvents slowly evaporate over hours, causing the resin matrix to shrink and collapse the gloss.
So skipping that 20% reducer doesn't just cause orange peel, it sets up a time bomb for gloss loss later.
Absolutely. The viscosity was too high, the resulting wet coats were too thick, and the solvents couldn't escape the deep film. Prevention is ensuring the 20% reducer is added.
Yeah, my remedy.
Assuming the film has fully cured or hardened, is color sanding, using very fine P2000 or P3000, and then buffing the surface to mechanically restore the gloss.
Runs and sags are usually easy to diagnose as application errors.
They are. The gun was too close, the painter moved too slowly, or there was insufficient flash time between coats, causing the first coat to move under the weight of the second.
And you have to let that cure hard before you fix it.
Rock hard. Then you carefully level it with a run block or specialized razor blade to knock the top off, and then sand and polish the entire area flat. Trying to fix a run when the paint is soft guarantees disaster.
And what about orange peel? That heavy, textured surface.
Orange peel is typically a viscosity and atomization problem. The primary cause is under-reduction, skipping the 20% reducer, making the viscosity too high for the gun to properly flatten the material.
And the other cause?
Low air pressure, meaning poor atomization of that heavy clear. Prevention is adding the mandated reducer and ensuring the air pressure hits that 29 psi target.
Now, peeling or delamination,
Yeah.
the clear coat separating from the base coat. This must be the biggest fear.
This is a complete failure of the intercoat chemical bond. The root causes are two major protocol violations. Either the painter exceeded the base coat recoat window waiting longer than 24 hours, or the base coat was applied so dry it was essentially powder, leaving no solvent residue for the clear coat to chemically knit into.
So it just sat on top.
It sat on top without bonding. The remedy, tragically, is stripping the affected area down to the primer or metal and starting the entire refinish process over. There is no patch for a chemical bond failure.
Finally, a soft film that fingerprints days later. It means the system didn't harden.
A soft film signifies an incomplete cure. The hardener, or activator, is the key. Causes include using an incorrect mixing ratio, so not enough hardener, or using old moisture-contaminated hardener, which degrades its effectiveness.
And if the hardener fails?
The cross-linking process halts. The initial remedy is often to force dry or bake the panel again, hoping to kickstart the remaining cure. If that fails, the chemistry has permanently failed and the film must be stripped off.
If we zoom out, the central philosophy of high-fidelity automotive repair is clear. It is a discipline where success is measured not by how fast you move, but by how rigorously you control every single variable.
That's right. Success is built from the ground up, starting with the mechanical efficiency of 3M Cubitron's precision-shaped grain in keying the substrate, right through to the chemical purity guaranteed by the Axalta 2-cloth method.
And that rigorous control has to extend through the top coats. We saw how success with Cromax XP solvent-borne base coat hinges on managing flake orientation through precise viscosity and the mastery of the drop coat technique. And success with the Nason 46500 high solids clear coat demands absolute respect for its complex chemistry. Specifically, adhering to the 20% reducer mandate for flow and strictly timing those 5-7-minute flash times to prevent latent solvent entrapment.
By managing adhesion, solvent evaporation, and the critical cross-linking process with this level of scientific precision, the outcome is a finish that not only matches the original OEM appearance, but actively rivals its durability.
It's proof that craftsmanship is simply applied chemistry.
It is.
That truly is the deepest dive we could take into a surface we rarely think about. We've spent the last 30-plus minutes charting a course through protocols where subtle chemical differences, like a microscopic salt residue attracting moisture through osmosis to cause blistering, or a P400 scratch disturbing metallic flake geometry, can absolutely destroy months of skilled, costly work. It's a battle won or lost on the molecular level.
Precisely. The margin for error is essentially zero.
So here is the final provocative thought for you to take with you. We have seen that such rigorous high-tech protocols are required simply to perfect the surface of an object we casually look at and rely on every single day. If failure mechanisms are so detailed, so hidden, and so dependent on molecular precision just in car paint, what other massive hidden microscopic failures, chemical, mechanical, or structural, are currently happening right now in the seemingly solid objects and structures all around us that we just haven't refined our protocols enough to spot yet? Think about that the next time you see a car with a perfect mirror reflection. Thanks for diving deep with us. We'll see you next time.